Hello, everyone. This is another video in the series on computer systems. This one's based on notes and slides from a textbook called Operating Systems, Internals and Design Principles by William Stallings. And in this video, we'll be starting Module 7 of the series, where we'll be talking about scheduling. And in this one, we'll focus on Chapter 9 from that book I mentioned in the last slide. And this is on uniprocessor scheduling. So we'll start with just looking at when we have single threads of operation running at any given time. Now, we'll have multiple processes, and we want to make it look like all of those processes are running at the same time. You know, when you kick off a program on your computer, whether you're running Windows or Mac OS or Linux, we don't want to have to wait for one program to completely finish before we can do something else. So we need to figure out a way to share a processor so that it looks to a user like a whole bunch of different stuff is happening at the same time. But if we only have one processor, if we can only run one process at a specific time, we have to figure out how do we share that processor? How do we schedule things so that it looks like things are rolling along all at the same time, even though we're actually sharing a single processor that's only doing one thing at a time? So basically, we execute a single process at a time on the CPU while others wait their turn. But again, we're not going to just have one process completely finish before another one can start. We're going to figure out a way to share the CPU. Now, when we talk about scheduling, we've got four main categories of scheduling that we tend to talk about. We have long-term scheduling, which is, are we going to add to the pool of processes to be executed, right? So we have all the processes that can be executed. Do we want to add another process to that pool of processes? Medium-term scheduling is the decision to add to the number of processes that are partially or fully in main memory, right? So, we have to have something loaded up into memory for it to run. Medium-term scheduling says, look, when do we load something up into main memory? And short-term scheduling is the decision as to which of the available processes are going to be executed by the processor. So once we finally get down to the short-term scheduling, this is where we're talking about, we have a pool of processes that's probably a smaller pool than all of the processes that are in the long-term scheduling pool, or even the medium-term scheduling pool, right? These are the ones that are loaded up and ready to actually be run by the processor. And with short-term scheduling, we're deciding, do we add something to which one of those will be executed next, at least for a little while. Now, notice that there's a fourth one down at the bottom here called I/O scheduling. This one actually means the decision as to which process's pending I/O request is going to be handled by an available device, but we're taking a little bit of a deeper look at that in Module 9, so we'll hold off on talking about that one, and you'll have a video on I/O in Module 9. So the aim is to assign processes to be executed by the processor in a way that meets our system objectives. So we're thinking about response time, throughput, processor efficiency, and it's going to this will change depending on what kind of system we're on, right? If I've got a server that's dedicated to great big jobs and we want to run them one after the other, I might not do a whole lot of swapping out of processes on the CPU. Right? If I don't have a user kind of sitting there looking at an interface, it's less important that everything appears to be moving forward all at the same time. It might make more sense for that particular scenario to have a much longer slice of time on the CPU for each process. Again, on a desktop, however, I want to be able to run multiple programs and have them at least look like they're making progress all at the same time. So there are different priorities and different objectives from system to system. But in any case, we've got it broken down into three separate functions. We have our long-term scheduling that processes go through and they get added eventually to the pool of processes that can be executed, the medium-term scheduling, where they get loaded up into main memory, and finally the short-term scheduling, where they can actually get some time to run on the CPU. Now, this diagram should look very familiar. We saw this back in our videos on processes and threads, right? And this will show us how a process can move from state to state based on scheduling, right? So if I create a new process, long-term scheduling can kick in to put it either into the ready suspend state or just directly into the ready state. That'll depend on the long-term scheduling decisions that are made. If it goes into the ready suspend state, then medium-term scheduling would kick in and load it up into memory and move it over into the ready state eventually. Once things are in the ready state, once these processes are in the ready state, then short-term scheduling decides which one goes to the running state on the CPU. And once again, the same thing applies as far as blocked processes. Right? Medium-term scheduling would determine whether we go from blocked suspend over to blocked. And then the exit state, of course, is over there, but that's not really a scheduled thing. That's something that happens as far as process management. These are the parts of that 7-state diagram that you've seen before. These are the transitions that are affected by our various scheduling decisions. So our long-term scheduler determines which programs are going to be admitted to the system for processing, right? We can have a bunch of processes in the new state that have not been moved into either the ready suspend or ready state yet, and it's the long-term scheduler that decides when one of those processes gets moved into the queue of processes that might actually start running. This controls the degree of multiprogramming. The more processes we create, the smaller percentage of time that each process can be executed. So we might have to limit that to make sure that the current set of processes get sufficient service, get satisfactory service. So the long-term scheduler creates processes from the queue when it can, but there's this little decision tree that it has to go through, right? We have to decide when can the operating system take on additional processes. Maybe we're maxed out on the number of processes that are able to run at a single time, so it's just going to have to keep a process in the new state and not actually put it in the queue yet. And then it also decides which jobs to accept and turn into processes. And that might be on a first-come, first-served basis, but there are other algorithms, and we'll be looking at different approaches that are mostly applied to short-term scheduling, but long-term can be kind of open for that too. And this is based on the ones they accept and turn into processes. There can be a lot that goes into the decision, right? We might have priorities attached to things. There might be something as far as the expected execution time, how much I/O does a process require. There can be a lot that goes into the long-term scheduler's decisions, but these are the things that that are going to be considered when we deal with long-term scheduling algorithms. Now, medium-term scheduling is part of the swapping function. The swapping in decisions are made based on the need to manage the degree of multiprogramming again. It's going to consider the memory requirements of the swapped out processes. And remember, this is where we're talking about going from suspend states, right? If we're going to go from ready suspend to ready or blocked suspend to blocked, this is the scheduling piece that's dealing with that. That's dealing with when do we swap something into or out of active memory so that it can be ready to go on the processor. Short-term scheduling, this is also known as the dispatcher. Okay, so you're going to hear that term a lot, so we want to make sure that we understand that when we hear about the dispatcher, we're talking about short-term scheduling. This is what executes most frequently and makes the fine-grained decision on which process to execute next. And what that means is it looks at everything that's basically in the ready state and says, well, which of the processes that are ready to execute do I put on the CPU next? Now, this happens when an event occurs that can lead to the blocking of the current process, or that may provide an opportunity to preempt a current process in favor of another. This can be clock interrupts, I/O interrupts, operating system calls, signals like semaphores, anything that tells tells the system, okay, time to put a new process on the CPU, the short-term scheduler or the dispatcher kicks in to make the decision as to which one that's going to be. Now, short-term scheduling criteria, a little bit different than the long-term criteria or the medium term. The main objective is to allocate the processor time to optimize certain aspects of system behavior. So we have to have a set of criteria to evaluate the scheduling policy, right? And we've got two kind of main categories of criteria that we deal with. We've got user-oriented criteria, and that has to do with the behavior of the system as perceived by the user, right? This is important on almost all systems, and that's the desktop example I mentioned before, right? And where there's a user looking at this interface and saying, gee, why is one thing hanging while another thing goes? Why does it take so long for a program to kick off, right? We want to, if we're dealing with user-oriented criteria, we want things to appear to be proceeding along at a reasonable pace and to have multiple things happening at once. Now, we also have system-oriented criteria. Now, that focus there is on effective and efficient utilization of the processor, right? So now we're talking about the rate at which processes are completed. On a single-user system, this is of minor importance, but think again about the server that I was mentioning. If we've got a server out there that's running and it's doing a whole bunch of big computational jobs, I might not care about things appearing to progress, because if I just dispatch a job to it, and then I wait for some kind of signal that the job is done, but I don't have to sit there monitoring things or doing other things at the same time, then I wouldn't have to care about user-oriented criteria. I just want to make sure that these big computational jobs get done as quickly as possible. So on that system, I might be looking at using system-oriented criteria instead. So how do we evaluate performance? Okay, we can classify things into performance-related or non-performance-related. Now, performance-related stuff is kind of nice for us. We're talking about things like response time and throughput. It's quantitative. We can measure it easily. It's just about how much time do certain very well-defined things take to happen. We might also be looking at things that are non-performance related, like predictability. These can be qualitative and difficult to measure, right? They don't necessarily lend themselves to a simple time measurement or something like that. So we have to be a little careful about what are we actually talking about as far as like our criteria goes when we're making decisions for short-term scheduling. Now, there's a table in your book, I believe it's on page 403, that talks about various scheduling criteria. So I want to kind of call this out and just make sure that you go take a look at that. This is table 9.2 in your operating systems book. There's also table 9.3, which is a great reference, and this has a whole bunch of different methods of selecting the next process, and it gives us some great information about throughput and response time and overhead for the various things like first come, first served, round robin, shortest process next, shortest remaining time, etc. And we're going to be taking a look at all of these different approaches that are up along the top row of the table here. So don't worry about exactly what they are just yet. We're about to go through and talk about them. But I want you to know that this table is there and kind of refer back to it as we go through these so you can see how these different approaches to scheduling do things in different ways. But before we get into those, let's talk about a little bit of terminology that we're going to need moving forward. We've got a selection function, and this is what determines which process out of all the ready processes is selected next for execution. So this is where we talk about what the dispatcher's doing. Right? It's going to run some kind of selection function that out of the pool of processes that are in the ready state, it's going to decide, okay, which one am I going to actually put onto the CPU next? That could be based on priority, resource requirements, execution characteristics, And if we're talking about execution characteristics, then there's some important stuff we got to keep in mind. We have W, which is the time spent waiting so far. E, which is the time spent so far in execution, right? So if this process is in the ready state, but it's been on the processor a few times, how much time has it actually spent executing so far? And S, which is the total service time required by the process, and we're going to include E in this, right? So the S is going to go down as the thing spends time in execution. Now, generally, this is going to have to either be estimated, right? If we've got some kind of profiling thing going on that can estimate how long a process will take, that can be applied, or it would have to be supplied by the user. But we have to figure that out and kind of attach that to the process in some way before we can use it as part of our selection function. Now, we also have decision mode. This specifies the instance in time at which the selection function is exercised. And we've got two categories. We can have non-preemptive or preemptive, and that basically means once we dispatch something, do we let it run for till it's done? Or are we able to say to a process that's running on the CPU, hey, stop, we're pulling you off now, and putting another process on in your place? So again, non-preemptive, once a process is in the running state, it will continue until it terminates or blocks itself for input-output. Preemptive means currently running process can be interrupted and moved to the ready state by the OS. And the decision to preempt might be performed when a new process arrives, when an interrupt occurs that places a blocked process in the ready state, might be just periodically based on clock interrupts. There's a bunch of different ways that processes can be preempted when we're dealing with a preemptive scheduling approach. So we're going to go through an example where we take a look at what different approaches do with this set of processes. If I've got processes A, B, C, D, and E, and I've got some arrival times and service times, right? Let's assume that the service times were supplied by the programmers. And the arrival time, we're just talking about time slices. So at time 0, right at the beginning, process A arrives in the ready state, and it's got a service time of 3. At time 2, process B arrives, and it has a service time of 6, and so on and so forth. So this is what we're going to be using as we take a look at the example on the next slide of how these things are going to look when we actually run these different scheduling algorithms on them. So let's keep that one in front of us. I'd recommend, if you have the book, keep these tables kind of open in front of you as we go through and look at how these different approaches work. The next one is figure 9.5. This is a comparison, and this shows under various different scheduling policies how these processes are going to end up being executed on the processor. Just a quick example, first come, first served just means that they're going to run, and they're going to run all the way through, but in the order in which they arrived. So we can see that here. A arrived at 0 and had a service time of 3, so it starts right there at 0 when it arrived and runs for 3. While that was running, process B arrived, but it couldn't run at time slice 2 when it actually got there. It's going to have to wait for A to finish. So it's going to start at slice 3 and run all the way to time 9. And in the meantime, process C has arrived. So as soon as B is done, C is going to start, right? It's just they just get in line. It's just a simple queue. But that gives an example of what this table tells you. So this is another one to keep in front of you so you can look back at this as we talk about these various approaches so you can see why this thing makes sense and how this table gets generated, right? How we can visualize what the scheduling policy looks like. And another table 9.5. We're looking here at a comparison of schedule policies, and so we're going to have some metrics, right? We want to be able to evaluate how our scheduling policies do. So the way this table works is we've got all of our processes, and we're keeping track of the arrival times and the service times. And then what we're going to do is under each different approach, so first come, first served, round robin with a couple different quantas, which we'll talk about when we get to round robin stuff. But we're going to keep track of what time did the thing finish, what was the turnaround time. Now, the turnaround time, it just basically means how long did it take to finish from when it actually got there. So for process A in first come, first serve, it arrived at 0 and finished at 3. And so the turnaround time, when we take 3 minus 0, which the turnaround time is 3. So when we divide those two in the third little row here, that's a 1-to-1, right? There's just 1.0 is what we're kind of talking about. With B, however, B arrived at time 2, had a service time of 6, so it didn't finish until 9. Because it couldn't start until 3. So our turnaround time was actually 7, right? From when it arrived to when it finished, we've got a difference of 7. So if we divide the turnaround time by the total service time, that gives us a 1.17. For process C, we had a finish time of 13. The turnaround time, because it arrived at time 4, right, and finished at time 13, we've got a turnaround time of 9. That means when we divide those two, the turnaround time by the total service time, it's 2.25. And now it kind of makes sense, is we'd kind of like our turnaround times to be as low as possible, when we'd like the ratio between turnaround time and service time to be as close to 1 as we can kind of get it. So that's why we kind of take the average of those things. We take the means over, at the far right column here, to give us an idea of what's performing better and what's performing worse as far as our scheduling policies go. So this is another one. Keep this in front of you so that as we go through these, you'll really understand why we're getting the numbers that we're getting. So now that we have all that in front of us, let's talk about some of these policies. And we'll just keep it as basic descriptions because I just want you to understand the methods that these things are employing, about how these things work in a general sense. Now, first come, first serve. This is the simplest policy. It's also known as first in, first out. It's a strict queuing scheme. So just think about a simple queue, right? Things just get to the back of the queue, and eventually they work their way to the front of the line. That's when they get executed. So as each process becomes ready, it joins the ready queue. When the currently running process ceases to execute, the process that's been in the ready queue the longest, right, that's the one that has made it to the front of the line, is selected for running. So this performs a lot better for long processes than for short ones, and tends to favor processor-bound processes over I/O-bound processes, right? This works pretty well if I've got a bunch of fairly long processes that don't do a whole lot. They're not going out to disk. They're not going out to a bunch of input-output devices all the time. And so that's our first one. And again, refer back to those tables that we just looked at to take a look and see what this means when we apply it to that set of processes that we looked at a few slides ago. Round robin, this one actually does use preemption based on a clock. It's also known as time slicing. Each process is just given a slice of time, and then it's preempted. Now, the principal design issue is the length of the time quantum or slice to be used. And that's why when you look back at those tables, we've got 2 round robin entries, one for a time quantum of 1, the other for a time quantum of 4. And you can see how that selection of the length of the time slice changes how these processes end up executing. Now, round robin is effective in a general purpose time sharing system, right, or a transaction processing system, but there is a drawback, and that you'll find out that this is a theme. There's always a drawback. It's relative treatment of processor-bound and I/O-bound processes. Now we have shortest process next, or SPN. Now this one's non-preemptive, so right, once something starts running, it's just going to run. Until it blocks itself for I/O or something like that. Now, in this policy, the process with the shorted expected processing time is selected next. So a short process is going to jump to the head of the line, which leads to the possibility of starvation. Remember when we talked about starvation as far as process synchronization goes? We could end up with starvation for longer processes here. Now, one difficulty is the need to know or at least estimate the required processing time of each process. So, if I don't have my users giving me this stuff, right, how do I estimate it? How do we figure it out? Another problem is even if the programmer does give you an estimate, what if it's substantially under the actual running time? Right? The system might end up aborting the job. So this one, again, it's got its uses, but it has its drawbacks as well. Now, shortest remaining time is basically a preemptive version of shortest process next, right? It's a preemptive version of the one that we just looked at. The scheduler always chooses the process that has the shortest expected remaining processing time. This one still has the problem of the risk of starvation for longer processes, but it should give superior turnaround time to SPN because the short job is given immediate preference to a running longer job. So for this one, because it's preemptive, and for all the preemptive ones that we talk about, remember when we make the decisions on do we preempt or not, we can do it based on a time slice where we time out, like in round robin, or we might be looking at when new processes arrive. So in SRT, when you're going through, like if you're doing practice on this, if you have to work a problem on this, keep in mind that whenever a new process arrives, if we're using a shortest remaining time approach, because it's preemptive, we need to reevaluate the remaining time for all the processes every time a new process arrives in the ready queue. So it's entirely possible that, I might have a process running that's been running for a while, but a new process arrives, I check the remaining time of everything, and if that other new process is very short, it might preempt, and it might not. Who knows? So we want to keep that in mind. Like I said, that's a point to remember because it often gets forgotten. We think we so often think in terms of the round robin time slicing that we forget that these algorithms reevaluate things for preemption when a new process arrives in the ready state. So let's make sure that we're doing that. Now, with highest response ratio next, we're going to choose the next process with the greatest ratio. This is attractive because it accounts for the age of a process. So shorter jobs are favored, but aging without service increases the ratio so that a longer process eventually gets past all these shorter jobs. So this helps us take care of that starvation problem. All right, so our ratio, we just calculate that by taking the time spent waiting plus the expected service time, divide that by the expected service time. So again, as the time spent waiting increases, we keep getting a higher and higher and higher ratio. So even if I've got a big, long job that, wouldn't get run maybe or might be susceptible to starvation under SPN or SRT with HRRN, its ratio is going to increase and get higher and higher and higher. And eventually it's going to age to the point where it's got the highest ratio no matter what. And it's finally going to get that time on the processor to get, to go ahead and run without falling prey to starvation. Finally, we have fair share scheduling. In this one, scheduling decisions are based on the process sets. Each user is assigned a share of the processor. So our objective is to monitor usage to give fewer resources to users who've had more than their fair share and more to users that have had less than their fair share. So for this one, we're kind of keeping track of how long processors that are part of a particular process set or processes that are part of a process set have been running. We're going to keep in track of the total amount of time they've been spent running. And if we see that, process set A has gotten a ton of time and process set B hasn't gotten very much, we're going to start prioritizing things out of process set B, right? So we keep things fair. We keep things kind of even. Now, what we've talked about here is long, medium, and short-term scheduling. Right? We want to understand what quanta, so time slices, are. So what kind of different quantum sizes can we be using for, say, round-robin scheduling? And we've described various scheduling algorithms like first come, first serve, round robin. We haven't gone too deep into a ton of the math. There's a little bit of math to do with HRRN. But the idea here, what I want you to take away from this is just understand in general how these work and make sure that you can go to those tables from earlier slides and understand why that example set of processes ends up being sliced up the way that it ends up being sliced up for each of those approaches.